I believe every human being is a potential coder.
Quizzical mind, somebody that likes to solve puzzles.
Someone who can work within a team.
I think you have to be quite meticulous.
You have to persevere.
Intelligent enough to understand the logic of the code.
Have empathy for their users.
The first thing is patience.
Likes to solve riddles.
A good coder is someone who can think through clearly and implement their idea into code.
10 years ago, we were coding for computers, but now everything is a computer.
A lot of the redundant and rudimentary stuff we do as a developer will be taken over by these automated processes.
Things like human brain interfaces and machine learning and neural networks.
Potentially a new language that doesn't even exist yet.
Still believe we have a bright future despite self-driving cars and artificial intelligence.
Interacting with a keyboard-less layout.
I think we're going to see a lot more voice interaction with devices.
Hopefully not computers coding themselves. This would be like, how it's called, the singularity, right?
I code because I love coding.
I code because I love, for me, it's like a brain puzzle.
Because I'm a builder and I ran out of Lego bricks.
There's a lot of creative juices that flow when I write code.
Because I like making things, basically.
Coding is fun.
It's a fascinating, wide-open field where you can do anything you absolutely want to do.
Having a problem that you turn into a solution through code is one of the most beautiful things in a job that I can imagine doing.
Good morning, London, and welcome to Oracle Code. My name is Gerald Fensel, and I will be the MC for today. Today is a great day for developers. We are back here in London for the second iteration of Oracle Code, and we will be talking about everything that modern developers want to and should hear about. Now, whether that's about blockchain or AI, whether that's about machine learning or microservices, serverless, databases, programming languages, DevOps, you name it, we got people flown in, thought leaders from around the world today to share their expertise with you. To help you out throughout the day, we do have a mobile app that you can install on your phone that allows you to follow along with the agenda. So if you just go to the Play or App Store and look for Oracle Events app, download it, and then just hit the search bar and add the Oracle Code London, it will download the agenda for you for today. That just helps you out throughout the day to see what's going on. Also, if you would like to stay in touch with your fellow developers out there around the world, and you are on Twitter, feel free to follow our Oracle Devs social media channel and follow the Oracle Code hashtag. And also, if you see something interesting today that you would like to share with your fellow developers out there, or something that you just discovered during the sessions and so forth, please retweet using the Oracle Code hashtag. Now, we got a lot of technologies today that help us to get to market really, really fast. And that's great, because no time ever has it been easier to just deploy something into production and deliver value to our users. However, once in production, it's equally important to actually keep fast. And our first keynote speaker will tell us exactly that. He will tell us about high-performance managed languages that you can use. He has been writing code in, I believe, assembly, C, C++, Java, and many, many more for many, many years. He's a high-performance and low-latency specialist. Please give a round of applause and welcome to Martin Thompson.
Okay, good morning, everyone. Yes, so I'm going to confess I am a nerd. I have been writing code for a long, long time, and I have been a manager at times, and I try to get out of it as quickly as possible, so I keep running back to doing these sorts of things. These days, I do a number of things. One of them I often do is work in the finance industry, and that's dealing with sort of trading, risk, all sorts of interesting problems there, but a lot of them have got high performance needs. And I'll go into teams, and these teams often have people who are writing in lots and lots of different languages, and there's usually lots of arguments in organizations about what is the best way to write high performance code. And because people who know me know that I started off with a lot of assembler and C and C++, and I've been doing Java since the beginning as well. So which language would I actually choose if I'm going to do something? I often get asked this question. For some reason my slides are not going forward. Can we fix them? Oh yeah, cool. So latency is my thing. So I actually transitioned the slide there, but the screen isn't, so we've got an interesting latency problem here. So if I want something to be fast, hopefully better than PowerPoint, but usually what I'm asked is, what would be my preferred language to do some of this in? And people are usually expecting me to say, well, it'll be C, or it'll be assembler, or I'll do it in FPGAs, or something like that. But whenever I'm asked, like, what is my preferred first choice language whenever I need to write, say, a high-frequency trading system, what would I choose? Well, if I choose something, and the slides are still not transitioning, do we know what's going on? Yay, we got... So I think that latency's running at about 12 seconds, I got that as. Oh, swap this over? No. Yeah, okay. Don't we love technology? It's great. Yay! Oh, come on. Yay! So now this joke is completely dead. What are we doing? So often I will come back and say Java is my preferred language for doing these things in. And many people are scratching their heads and thinking, why am I saying this? This makes no sense at all. And they usually follow it up with, well, why would you build a low latency application on a GC platform, something that has garbage collection? That seems incredibly crazy. And usually at this stage, you'll see all of the C++ people in the room with this sort of face looking at you. And they're kind of, really? You're going to use Java for doing high frequency trading? This is insane. Let's put some context around this first. So before we go forward, I want to make it clear up front that a managed runtime is not always the right choice or the good choice for certain types of things. And for example, if I was doing latency arbitrage where I'm trying to trade at the absolute fastest I can within a given market, would I be choosing Java? Well, no, I wouldn't be. Would I be choosing C? No, I wouldn't do that either. I wouldn't even choose to do assembler. Most likely, you'll be doing this in hardware, in an FPGA or an ASIC. So it's a different kind of world. So we're moving above that where we want to be really very fast, but not absolutely at the fastest. And so if we're going to take this up a level, what about if we're doing native languages? Are they actually faster than a managed language? This is a kind of interesting question. And if I ask myself, which one would I choose if I wanted to be as fast as possible, could I go with that? Well, to be honest, you could do this in C or in assembler, and it will be faster than any managed language. But there's an interesting question behind that on what it is. It's like, do we have enough time? If you've got the right skills and you've got all the resources in a team to build the absolute best solution, that's possible. But that requires a lot of resources that are not just necessarily hardware for you, it's skills, time, whatever that's in there. So before we dig into that, let's explore this from an evidence perspective and see what can our runtimes do for us and compare that to what would a native language do for us and see how they compare against each other. So let's start off and explore something. So we're typically talking here about CPU versus memory performance. I'm not talking about going to network, going to disk. At that stage, the language starts to become less relevant. It's usually a question of the libraries, the OS calls, the different things we're dealing with at that stage. Stick with things that are running in memory, and we're going to be working doing computation against that memory. So, quick question. How long does it take to add 2 integers on a modern x86 CPU? Any ideas? Sorry? One clock cycle, yeah. Someone is aware of these things, yes. It only takes 1 clock cycle whenever you've got 2 values that are in registers. You want to do an addition to get a result from that. Go read Anger Fogg's stuff. It's great. You can dig into this in more detail. Now, look at what's involved in it. It's actually a little bit more than just adding 2 numbers. We typically have to load numbers into registers in the CPU. We've got to perform the addition. We then will take the result of that from a register, store it back in memory. There's a number of different steps to this. Now, imagine if we're going to go across an array and we're going to add up all of the elements in an array to do a summation across that. Look at what it will be the average time per instruction or per step in this process to do that. So I'll add up one element, I'll go along, add up another one, keep a running sum. The average cost per time. And let's start measuring this and see what we get. So average time per element across a whole array of integers. Say that array is 1 gigabyte or 2 gigabytes in size. If I ran a benchmark to do that and measure the average time per operation, I start to see that it's 0.8 of a nanosecond. Now, if this is running on a 3 gigahertz CPU, that's just over 2 cycles. This sounds kind of crazy. So like really? Less than 1 nanosecond? You start thinking, well, I've got to load in 2 values in the registers. I've got to sum up the value. I've got to get a result of that. I've got to write it back. I've got to increment the loop counter to go forward. So there's a number of different things. So 2 cycles doesn't fit with the number of steps in that. There's probably about 10 instructions needs to be processed, and we're doing it in 2 cycles. So how do we achieve that on a modern CPU? Well, typically, if you've gone back and you look at your computer science course at university, like I did do computer science at university, but that's way, way back now, 25 plus years ago. We learned about von Neumann architecture. We learned about the fact that we have one arithmetic and logic unit inside our CPUs. That is not the case anymore today. This is a Haswell CPU, circa 2014, so not even the latest. So about 2014, inside a single CPU core now, we have got many execution units, and we have multiple ports on a scheduler inside that CPU executing those instructions. So like, we have 4 different ALUs. We have numerous address generation units where we can load and store data in and out of our CPU. So our CPUs can be doing an awful lot of things in parallel inside our streams. And this is even for single-threaded code. We get a lot of parallelism in single-threaded code. So think about incrementing the loop counter going over that array is independent of the summation of the values in the array that could be happening at the same time, that could be happening slightly out of order, but that can be done in parallel, and our CPUs can give us a lot of throughput because of that. As a result, we can be summing up at 1 element per step we're doing is taking less than a single nanosecond on a 3 gigahertz plus CPU. So much, much faster than we expect. But let's answer a different question. What if the access pattern is different? So if I'm running through that array from beginning to end, that's a nice sequential pattern, and things are all laid out in order. What if I start doing other things, like randomly jump around inside an operating system page, randomly jump around across the whole heap, or make it really interesting where the next step that I take is dependent on the value of what was in the cell that I previously read? This creates things in a very different scenario. So I'm going to do exactly the same amount of work, but I'm going to use different access patterns. Now, if I put a benchmark to do that, what sort of figures do I get? Well, I get these results. So my sequential pattern, extremely fast, less than a nanosecond per operation. Jumping around randomly across all cells within an operating system page, I jump up to 2.7 nanoseconds per operation. If I do a random step within that, but I take the previous value into the next step calculation, it jumps up to 7 nanoseconds. Then if I go randomly through the whole array, I'm looking at sort of just under 20 nanoseconds. And if I'm going randomly through the whole array, but where the next value is dependent on the previous value read, I'm now up at 90 nanoseconds. That's 2 orders of magnitude difference for the same amount of work. What you start to see is the memory access patterns and cache misses matter much, much more than the CPU instruction time that you spend. And a lot of what our language is, when we compare like for like, we're comparing instruction processing, we're not comparing memory access. That is where the dominant cost is. In the modern CPU, you start to think that it doesn't matter really how many instructions you execute, it matters how many times you cache miss, and particularly these dependent cache misses. Because we talk about these as being data-dependent loads. Pointer chasing is another way you hear this term. So things like your linked lists, your trees, these sort of data structures are the expensive operations that we have today, not just the instructions. The additions, the subtractions, the multiplications, all that sort of stuff is effectively just a rounding error. It's noise in the cost. Unless you're doing high performance computing and just doing pure number crunching, that generally doesn't factor into what we're dealing with. Now, here's another interesting question that we're going to do is like, are we actually agile, and what does it mean to be agile? If I'm compiling stuff ahead of time, I have baked in all of my assumptions about the code that I'm going to execute at the time I compile it. It says nothing about my data access patterns. It says nothing about the layout of that data and the data structures I'm going to be working on. I can't change that later. It's baked in at the time I compile. But if at runtime I can make decisions based upon what data I'm actually seeing, I'm actually much more agile from a runtime perspective of my code. Like this whole thing about like, are we doing agile or are we not doing agile? I find it fascinating. If you look at the mathematics behind agile, it all comes down to things like Little's law and queuing theory and all that sort of stuff. Doing stand-ups every morning does not make you agile. Understanding some of the fundamental theory and being able to apply it is really what makes you agile. So let's look at what possible runtime optimizations we can have in our code. So if we can profile our code at runtime, seeing the real access patterns that we're going to use, we can start making some interesting optimizations that we cannot make at compile time. But what's even more interesting about that, because I can do certain things at compile time that may be a good bet but may not be a good bet at runtime, I particularly have this interesting thing where can I revoke the bets that I've taken. So if I think the code's going to go a certain way, and it turns out it does, I win the bet. If it doesn't, I can revoke it and back out. And runtimes allow us to do some of these sorts of things. Now, when I'm talking managed runtimes, Java is a managed runtime. C# runs on a managed runtime, the CLR. We've got JavaScript, we've got Smalltalk, we've got lots of these things. A lot of this stuff has been around for a long, long time. Like our first garbage collector came with Lisp, done by John McCarthy 50 years ago. Most people in this room probably weren't born then. Maybe your parents were just kids at that stage. This is the sort of thing. This stuff's old. It's not exactly new. So let's dig into it and let's see what options do we get and explore what optimizations we can apply. So our code's full of branches. So we've got some method foo, and inside that method I've got an if block that's got some condition. I've got code before it and code after it. What can we do when we profile this at runtime, and what can we do with the layout? So I've got a block of code before the if and including the if itself, because that will always exist together as one block. I've got a block of code inside the if itself, which I may or may not run, and I have a block of code afterwards. Now, if I always take that if condition, it makes sense for that code to be laid out nice and sequentially in memory, because our code is just data that sits in memory the same as our normal data structures to the CPU. It doesn't really matter. So remember the nice sequential pattern? If you would drop straight down through that, that would be really good. But what if we hardly ever go into that if statement? We'd have to jump over it, and we're jumping over it dependent on the value of what the condition is. We have a data-dependent load. Now, if we were to profile our code at runtime and realize that we hardly ever take this if, like maybe that if is a check on a return code that is generally never a failure case, so it's error checking. We don't want to go in there because that would be an exceptional case. We want to jump over it and go straight to there, but then the jumping starts to cost. What if we laid out the code so that we had block A followed by block B, and a special case for block A followed by block C, and a special case for B at the end of it? We could do that if we profile our code at runtime. Now, at compile time, if I'm writing C or C++, I can hint to my compiler that whether a branch is likely or unlikely to be taken, and I can deal with that. Our CPUs have got branch predictors, and that's cool as well. They can start to guess these things in advance. But the layout is something we can't change easily. We have to deal with it one way or another. So our runtimes can lay these out based upon real data that we have from our running programs. And some branches are more subtle than you think. So you may be using a ternary operator. So if I is greater than 7, I'll assign A to result. Otherwise, I'll assign B to result. Now, if it's a case that, like, say, it's high 90% likely that A is greater than 7, or that I is greater than 7, we will assign A. That's great. We could just rely on branch prediction and go with that. Now, what if it's 50-50 and we don't know? What can we do in that case? Well, our CPUs have got different instructions. And so, for example, we can use a thing called the CMove instruction on x86, which is non-branching instruction. It costs a little bit more than just doing the straightforward assignment. It's conditional on that, but it's not a branch that's going through the branch predictor. If we know the probability of I being greater or less than 7, we can choose whether we go with branch prediction or we can choose whether we go with the CMove instruction. We can't do that at compile time. If we're doing it ahead of time, we can do this at runtime. So it's kind of cool and interesting things that we can start to do. This sort of stuff that our Java runtime is doing for us right now. But there's a little bit of an elephant in the room when you come to branches, particularly in Java. Switch statements aren't profiled. So up until now, we've had no profiling of switch statements. And if you see any really good high-performance code, you'll often find the common case in an if statement at the top of a block, especially when doing state machines, followed by a switch statement afterwards. And this is to help out our JITs. Well, come Java 11, we're now going to get profiling of switch statements as well. So these things can move on over time and they get better. So it's not always perfect, but they can grow and get better over time. If you're running this through LLVM, you get much better profiling and nicer results of that. That's branches. We also can be inlining methods. So I've got foo and I've got bar in this code. Block of code, call a function, another block of code. So my first block would be the code at the top. The call to bar would be included. Now I've got to jump across to them wherever in memory bar happens to be as a method, execute that, and then return back. But also as I call that function, I've got to pack up all the arguments to that function, put them on the stack, do a jump to there, execute the code by unpacking the arguments off the stack, using them. When I finish the code, I'm probably going to have a return value, which I've got to pack back onto the stack, send it back again. So there's a lot of work inside there. Let's say bar is just a small, simple method, and you're calling it all the time here, and foo is a hot method in code. Well, what we could do is, rather than do this jump, jump, jump back again, we could just call the block A of code. We could inline directly into the body of foo, the code for bar, without even the function call overhead, and then execute B afterwards. Nice, linear, straight through, don't take the function call overhead. That's really quite nice. Why don't we do this everywhere? There's an interesting trade-off. So in our C++ or C code, we can choose to do that. We've got the inline keyword. We can do these sorts of things in static languages. If we do it everywhere, we end up with an interesting problem of code bloat. Our instruction cache on an x86 processor is only 32K. And there's a micro-op cache behind that, which is only 1.5K. So tiny little caches that we want to make really good use of, so we have to choose which code we do inline, which code we don't inline. In a large code base, can you guess that all up front when you've got millions and millions of lines of code? If you've got something at runtime can measure it and see what is the hot code, where is it worth inlining, you get the wins without wasting the time and wasting the AI cache elsewhere. A runtime can do this for you. Take it further. Cliff Click, who wrote the JIT compiler for Hotspot for C2, he talks about how inlining is the optimization, because not only do you see it from the inlining, you can then apply lots of other really interesting optimizations once you've inlined that code, because you've got a larger code block now that you can choose to optimize. For example, let's say we hit loops. There's loads of studies that show that sort of 80+% of time in our code is spent inside loops. So how we craft our loops is very important to performance. And so we may be like iterating over this array for a given length, and then apply some operation to it, like call bar in this case. Well, I'm going to take the overhead of the loop every single time round here. That's a big cost, particularly if, say, bar is quite small. Well, our compiler could choose to unroll that loop and do a number of iterations of it. So maybe go to 4s or 8s or something like that and do those. And so you've only got the loop overhead once every 4 or once every 8. We can get a lot of benefits from that. But again, think about the code cache, the bloat that can be caused from it. You don't want to do it everywhere. You've got to choose the places that make sense for that to be done. A runtime can measure that and start to do interesting things. It can also do interesting things on the particular operations inside there. For example, we get these things called intrinsics. So what an intrinsic is, the compiler is looking for a particular signature in the code, and depending on the CPU instruction set that's available to it, it can swap some of these methods directly for an assembly level instruction that can deal with this. So for example, integer.bit count, if you have a look inside there, there's a lot of shifting and masking and bit twiddling that happens to count the number of bits set in a given value. But if you know you're running on an x86 processor that's young enough to support SSC 4.2 instruction set, there's an instruction called pop count. And that's a single cycle instruction that will count the number of bits in a word. But if you've got an older processor, you don't have that. Well, we can decide to run on an x86 processor, and if we're running on one of the later ones, we just have the JIT automatically choose that instruction as opposed to doing it the old way. If we were to do the statically compiled, we're having to choose which platform we're targeting rather than letting the runtime decide based upon what it's running on. We can get these sorts of benefits and even do it depending on the data that's been passed to. Polymorphism, like we write object-oriented languages. This is one of the benefits of programming something like Java is we can have a core algorithm, we can extend it with new types later on and not change some of the code that runs our core algorithm. So for example, I want to iterate over an array of shapes and draw them. I might be doing a GUI of some type, and the draw method is going to be subtype polymorphic in that we're going to have multiple implementations of that. Now that's an interesting problem because with these sorts of things is you've got to work out which method we're going to call at runtime. It's a reasonably interesting and tricky problem. We may have lots and lots of types there. We may only have one type. What optimizations can we deal with? So we may have a case where in the first case we have got hundreds of types and we will take the cost of a jump table to work out which type we're dealing with. In this other case, maybe the isVisible method is on a base class and not on the subtype, and there only is one version of that. We don't need to put a jump table in place. We can work this out by how many implementations of that method there are and optimize accordingly. So in the isVisible method, that may be so simple that we don't ever need to subtype it. We have only one implementation of it, but it's actually a polymorphic method. So it could be overridden and we don't know that, but at runtime, we know that it's not overridden, so we can take advantages. Whenever I'm writing C++, this is one of the features I most miss. If I know I'm going to extend something, I have to make it virtual. That will bring that cost with it forever. In Java, I can just deal with the default type, which is polymorphic. I can make it final to prevent the subclassing of it, but by just leaving it in the standard form, the runtime can optimize this. If you're writing C#, you don't get quite the same benefits. They don't have this optimization. So interesting little options that come in there. So how can we do this? Well, a runtime does a thing called class hierarchy analysis. If you don't subclass that method, it'll know that there's only one implementation of it. How do we know when it's subclasses? When we load another class that does that, so we can trigger during the class loading process that we have a new version of this. We can then revoke the bet that we've taken that there only is one implementation of this and take it back and replace it with another implementation. This is I can take bets, I can revoke them, I can do nice, interesting things. And depending on how many implementations, we can make this more or less efficient. So if you've only got one, we can do a monomorphic implementation, which is very fast, can be inlined, highly optimized. If we've got two, we can have a bimorphic implementation that maybe only has an if statement in there and call one or the other based upon that. Typically in Java, if we've got 3 or more, we become megamorphic at that stage and we put a jump table in place to go and find it. If you were using V8, for example, writing JavaScript, they go to 4 before it goes megamorphic. The Zolzing compiler will do it with 4 as well. So we vary around how many implementations of these before we need to go megamorphic and put a jump table in, which is the data-dependent load. But even at that, there's other benefits can be had. What if one type is way, way more common than all of the others? We can do a thing called inline caching. We can cache the common type and go to the jump table for the others. Again, based upon data at runtime, we can do all of these quite cool things that makes our code fast. And we don't have to change anything or do anything weird. So let's get around to garbage collection. It's kind of one of the elephants in the room when we want to have low latency. Now, before we get into this, let's look at some of the principles behind it. And one of the most important things to consider is that objects' lifetime is directly proportional, or the object cost of keeping it from a garbage collector is directly proportional to how long it lives. So if you want to design code that's fast but uses objects, make sure they live as little time as possible. So to steal a line from Billy Joel, only the good die young. We want our objects to die young as quickly as possible. And this is because of discoveries we made around generational garbage collection and go right back to the Smalltalk days. So our heaps are typically laid out something like this. We have a new generation and an old generation, and we've got survivors and stuff. I'll dig into what the different parts of this are and how it works in a second. So it's based upon this whole concept of only the good die young. But let's add a little bit more context to this before we drill in. Scary picture. Typically, our modern servers now have multiple CPU sockets. So socket here, socket 1, socket 2. We've got multiple cores within a socket. But what's really interesting about this is we now have memory that's socket local, and we have to connect across these sockets if we want to communicate between them. So if we look at this, like this link here, this QPI link that links our two sockets is the quick path interface. If I'm going to local memory down here, it's at least 65 nanoseconds. It's the same on the other side. But if I get across the socket to go to the other memory, I've got to add 40 nanoseconds, absolute minimum for going across the quick path interface. This is because we're separating it and we're allowing things to scale up. It's called NUMA, non-uniform memory access. So we want to be staying local if we can and not go remote. But what if we look inside one of these sockets on its own? Does this get any simpler or more scary? So here I'm sort of in core 1 to N. Like we can have 20 plus cores on some of our x86 machines. What happens if we buy a 24-core Broadwell machine? What do we get in a single socket? Another scary picture. It's really scary actually because you think that you've got a single socket. You've got all of the CPU cores around the outside of these rings. You've got cache segments on the inside of the rings. This is one of Intel's own slides. And notice these rings are interconnected. They're actually two separate regions on the same socket connected by a network switch. Yes, I actually said that correctly, a network switch. Our CPUs on socket today have a network that connects the CPU cores to the cache segments. And if you're local within one of these segments, performance is different from if you go remote across these. And then you've got to go remote across the sockets on the machine. So this is all very fractal in how it's laid out. We'll see how some of this comes into play. So let's look at the Eden within our garbage collection region. So Eden is where all objects are created. So we will create an object inside Eden, and we in fact create them within a sub-region of that called a T-lab, which is a thread local allocation buffer. Each thread gets its own buffer to allocate its objects out of. Within that, it's a very simple operation. We just apply about 10 instructions to bump forward a pointer for the region that we've just claimed, and we create an object within that. Each thread has its own region, so there's no contention between the threads as we're allocating objects. This scales really nicely. But some interesting consequences to that. If you run with hundreds of threads in your machine, you may have 99 plus of those threads that are allocating at a nice modest rate, and they've only used up a small percentage of their T-lab, and you've got one really greedy little thread that allocates a lot. Once it uses up its T-lab, it needs to get another one, needs to get another one. What if it can't get another T-lab because there's no space left in Eden, but all of these other T-labs are all just partially used? We have to do a full collection of the young generation at that stage, so we trigger garbage collection. So going with lots and lots of threads is not necessarily a good thing for many, many reasons. Once we trigger that garbage collection, we get into the next phase of things where we'll move on from that. But think about how things are laid out here. We get nice locality of reference because we keep the objects together, especially if they're living for a short time. We don't have the facts like what's known as false sharing between threads, where cache memory is being shared between them because they're isolated and independent. And some of our collectors can be NUMA aware. So remember the scary pictures I've just shown, that if you're allocating the T-lab on the memory region that your thread happens to be running, it's nice and local. But if it's not nice and local, we have certain problems. So if you happen to be running, like, say, the Oracle throughput collector, and you're using the use NUMA flag, we can benefit from that. Unfortunately, if you use G1 or you use CMS, you can't use that NUMA flag, so we can't always have the nice things. So there's consequences to our different decisions. Going with some collectors, you can benefit from some of the memory layout. Other collectors, you can't benefit from it, and kind of be aware of that. So then we do a collection, and if we've got the memory available for a period of time, we need to keep it, and so we're going to move it into one of the survivor spaces. So garbage collection, terrible name. We do not collect any garbage within our garbage collectors. We harvest objects that are still referenced. Again, I'm going to make lots of appeals to our industry to please give things sensible names. It doesn't collect garbage. Things like, we don't have random access memory. We have arbitrary access memory. If we just got randomly access it, we could have just any junk come back to us. So please, my appeal is, if you're going to ever name something, at least pick up the dictionary first and look up the meaning of the word before we go and sort of stick that moniker on something. Software maintenance is another one of my things. Things don't need grease, they don't wear out. All these sorts of things. We adapt software, we do all these sorts of interesting things with it. So maybe one day we'll grow up as an industry and we'll actually read the dictionary before we put a name on things. So if we're going to keep something, it'll be copied from the Eden space into one of the survivor spaces when we do a young generation collection. And then we'll continue on. If we do another young collection, we'll copy from one of the survivors back to the other ones. So things get copied backwards and forwards between these survivor spaces, and we retain them as long as they're still referenced at that point. And that's still staying in the young generation. So there's different things to think about here. It's like, oh, what is our aging policy? How many times are we going to copy things between survivor spaces? I think every time you copy it, that's got a cost. It's going to be doing some work. But there's some nice things. So whenever you collect all of your objects, you're going to compact them all together in the survivor space. Whenever you collect again, you're going to copy them all to the next survivor space, but we're going to keep them all together. It's all going to work nicely. And many of our collectors are parallel for this. They're actually very well written parallel collectors, so they do this stuff reasonably quickly. Although it still has a cost. And the main cost is attributed to what survives. And whenever we survive stuff, there's a number of components to it. There's the copy cost, but there's also fixing all the references to an object. So the heavier referenced an object is, the more cost there is to keeping it alive as well. So if we've had something copied backwards and forwards for a significant period of time that passes the aging policy, we will then move it to the old generation. And we take another step forward at this stage so we can do other things. As we move to the old generation, typically on the publicly available collectors that are open source, is we're dealing with things like we can have concurrent collection. Now, we can't have concurrent collection on the young generation with what's typically available. There are commercial collectors that are concurrent for the young. But the concurrent in the old means that we can collect it whilst we're continuing to do work. And so that can go forward. But we can also start to do cool things like, as we move stuff from the young generation to the old generation, if you're running something like G1, for example, we can find strings that are duplicates of each other, and we can deduplicate, so we can have the string objects point to the same character buffer, and that will save us memory. And the less memory we have, the better the chances are that things will be in the same operating system page, and we'll get benefits from doing that. So keeping the memory down is a kind of good and useful thing. But let's look at the collection phase itself and what's one of the impacts of that. So say this is the state of my young generation, and I now need to do a collection, and this is the state of the objects that are still referenced. The rest of that would have been full of objects, but all of those other space is not needed. It's objects like iterators, temporary strings, all of that sort of stuff that we no longer need at the end of our collection cycle. So we want to collect these things, and we're going to move them to one of the other survivor spaces. Well, how most collectors work is you tend to do a depth first copy. So if we look back at this, like, so let's say this was an array pointing to lots of other objects, like maybe an array list, for example. What we'll do is we do the depth first copy, so we find all the children of that object, and we copy them across, all nicely compacted together, and then we'll copy across the array itself. And this is how the collection process will happen. But think about the implications of that is we had memory randomly all over the place here, and now we move it all to be nicely compacted together. We have got it all typically within the same operating system pages, often within the same cache lines as well, and it's all nicely laid out. So we get much more friendly access. We go to those lower levels of numbers rather than the higher levels of numbers. So the fact that you're doing work during garbage collection doesn't mean it's all total cost. That cost can pay back in how it saves us time later on. But there's this elephant, there's the stop the world side of it. So as we do a lot of the collection with many of our collectors, is we have to stop the world. We've got to stop all of our threads, bring them to save point, do the collection phase, and then start them all up again. This is something that we all get to dislike, particularly in finance where we're trying to do low latency. So what alternatives do we have, and where do we go? Well, typically you'd be dealing with some of the concurrent collectors for the old generation in the past, like CMS, for example. We then had G1, and the reason G1 was brought in was because CMS actually works quite nicely. It's a good algorithm, but it's got this bad case that it falls back to is what happens if it cannot collect the old region to a point where you've got a big object that needs to go into it, but that big object doesn't fit because the space is all fragmented. You've got lots of little holes. It doesn't compact the old generation and how it works. That's how CMS works. So G1 takes a different approach. It cuts memory up into lots of little regions. And the idea with it is, it's called G1 because it tries to find the regions that have the most garbage in it, garbage first. The regions that have the most garbage will be the ones that will be targeted for collection. And so it'll split it up into all of these little regions. Some will be the Eden space, just like before, it's generational. Some will be the survivor space, some will be the old space. And it's looking for which of the old space versions have got the least numbers of objects that need to be retained, and from there it can collect those. And so it breaks the problem up of the long GC pause up into a number of smaller GC pauses. So it is still stopping the world, it's just doing it more frequently with smaller individual pauses. So it's amortizing that out. And sometimes we've got really big objects, we need to join together a number of regions to make them humongous. And so we put those big things in there. There are alternatives as well. So one of the ones that I've worked with that I like to use is Azul's C4. It's the only one that is truly concurrently compacting that's out there. And you effectively don't get any user noticeable pauses that are in there, where it's collecting in the background all of the time and compacting the memory at the same time. And so that's available, but it's a commercial option. There are some other interesting collectors coming down the line like Shenandoah, and a very similar one to how Azul works is going to become open source in the future. So we're going to get lots of more and interesting collectors in this space as we've kind of learned from it. So let's look at, if we compare dealing with this stuff using management of the memory versus we're going to do it manually ourselves, what are the things we need to think about? So like in the managed GC, we have to care about the GC implementation itself. So we have to be getting the characteristics that we expect. And that has certain implications, like we've got to mark cards, we've got to deal with read and write barriers. There's an overhead to all objects requiring a header. And stuff has to happen in the background, which requires CPUs and memory to do that. So we get benefits, but there's a cost. On the native side, it's not black and white for what we have to do or not do. Like all Moloch implementations are not equal. There's quite a bit of variability in whenever we deal with this. And actually, the real elephant with most of this stuff is object allocation is not the problem. Object allocation is really easy to do. Object reclamation is the hard part. And it's the hard part for both native languages and for managed languages. So how do we deal with that? On the native side, we end up with having to group objects into sizes, and we use arenas and pools and ways of dealing with that. But we can get wastage inside those pools, so we don't use all the memory so well. They're also very prone to fragmentation, and fragmentation can have quite a cost on chasing data-dependent loads. Debugging this stuff is really hard. So one of the reasons I like writing on a managed language is I'm much faster at delivering because I spend a lot less time debugging because I get things caught at runtime rather than having to chase down my memory leaks. And particularly if you're passing objects between threads, this is where managed runtimes really win out over your native languages. Native languages, passing memory between threads requires quite sophisticated techniques and also things like atomic counts on things which really slow down how things are happening. So if you're passing backwards and forwards between threads a lot, it costs a lot. But what's really interesting for me is where's GC going? Like, when we look at the fact that we're collecting memory, we're managing it, so we're starting to see compaction, we're starting to see deduplication. Could we take control of layout itself and make quite a difference? Like in C or C++ or some of the other native languages, one of the huge benefits is you can group things together that should be together. So for example, I can have an aggregate object, like I can have a person, and the person can have a date of birth, and they can have a favorite color and things like that. These other objects that they're related to are going to live and die with the aggregate. Like your date of birth is not changing, your age changes because it's a function of your date of birth and what the current date is, but your date of birth stays the same. So if you were to move that object through memory, you want the whole thing to move together. And you don't want to be doing a data-dependent load chasing off through memory for these sorts of things. Object layout was a proposal that Gil Tene and I put in to try and address that. It hasn't been sort of adopted, but as part of the research behind that, we made an interesting discovery. And so we started discovering that what if, rather than trying to programmatically decide ourselves which should be inline, which should be an aggregate, what if we had the garbage collector realize which are actually aggregates and start putting objects together based upon their usage? So for example, if you have an object and it's got a final field that references another object inside there, and that object never escapes the encapsulation of the parent object, why not just treat it as a single thing? We did this and we got quite surprised that the runtime was making decisions that we never even thought about and put stuff together and got huge and interesting performance wins. So I think we can see the future going off down this. There's also a number of PhD projects have happened in this area, so we could be getting some really nice benefits come in there. Algorithms and design is kind of one of the last topics I want to talk about here. Is you think about where do we get most of the performance from in our application? And so I'm going to ask this simple question. It's like, what do we think is the most important thing to getting good performance in an application? Anyone shout out? Sorry? Algorithms? Up there, I would say it's not the number one. Clean code. Clean code. Any others? Fragment. Yes, there's a number of things. What's common with everything that you've said You're missing what you need most to achieve any of those things. It's time. We need time ourselves working on a project to find the good algorithms, to decide how it is, how to get clean code as you put time in. Like, how often do you work on a project and think, I have too much time? It just doesn't happen. We don't have too much time. I love this quote from Blaise Pascal. If I had had more time, I'd have written a shorter letter. This applies so much to code. Go back, revisit and refine your code. You can often make it smaller, more succinct, more efficient. That is truly how you get really high performance code. You'll do lots of other things, but you need the time to do that more than absolutely anything. Like, if I'm looking at performance, like a lot of this sort of list of things that I would be doing to try and make my code faster, like the classic one is just avoiding duplicate work. Like, if you've got one language that's 10 or 20% faster than another, if you do something twice, the whole thing's irrelevant to which language is faster. It's the sort of basic things that we're dealing with. So we can deal with all of these sorts of things, but the most important thing is having the time to do a lot of these things and do it well. And if you've got a very large code base, can you do everything really well? Like, as a human, we're going to be feeling all the time because we can't deal with like the million-plus lines of code that many applications are and know that we're doing the right thing all the time in the right place. We need to get computational support to help us with those sorts of things. And that's where some of our managed runtimes can come in to do this. So kind of got a simple little story here. It's like, I've been spending a lot of the last 5 years working on a messaging system called Aeron. Now, we have built this in a number of different languages. We did it first in Java. We've ported it to C++ and to C, and we have seen ports go to C#, Go, and other languages that are out there. And people would often ask me, why did you do it in Java rather than C to begin with? And my answer to that is really, really simple. It's all about time to performance rather than absolute performance. It's easier to prototype something quite often in a managed language. There's lots of things that are annoying. So as we did this, I really have come to detest NIO. NIO is just an abomination, but we have to suffer it. We live with this over and over again, and I really wish somebody would improve it. Like Java 11 or Java 10, we've now got var. Yay! We still got NIO that sucks. Please, someone make this better. But what's interesting with the time to performance is, like, so if we look at the fact that we developed a lot of the algorithms in Java to begin with, we developed some of the algorithms almost at the same time in C++. When we run the first version of it, the real surprise was which one was faster. So before we go through a cycle of profiling and tuning, when we compared the Java to the C++ on first pass, and Todd and I have done a lot of this, so we're well used to writing in multiple languages, we discovered that the Java implementation was actually faster than the C++ implementation. Now, after profiling and visiting that, we were able to make the C++ implementation faster than the Java, and that took more time. But it was interesting that for the same amount of time and effort being put in by people who are comfortable in more than one language, the Java code was the fastest before we go through a lot of the tuning cycle. So there's a kind of really interesting lesson to go through there. We've seen some of this with moving to other languages. Then you get into the refinement stage that you can ultimately get faster than that. So I keep saying it to say, Java gets me to the point where it's going pretty quickly to begin with, and then it actually starts to get harder and harder to get more performance because it becomes a little bit more painful to tune and when we profile it. C is kind of the other way around. Is that initially it won't be going so quick, but you get so many options you can tune and make it better. But you're trading off time against doing some. And in, say, something like high-frequency trading, often being first into market matters much more than being the fastest overall, so to make the money back on this. I've talked to lots of teams about these sorts of things. So I'd done a piece of work comparing a lot of the managed runtimes a couple of years ago, and I interviewed the V8 team, I interviewed some of the Java teams, and I also interviewed the C# team. And one of the standout things for them was their move to the Roslyn compiler. So in C#, the compiler used to be written in C++. They made the decision that they were going to write the C++ C# compiler in C#, and that was the Roslyn project. That turned out to be hugely beneficial. And now they've got a compiler that's much faster than the previous version. It also caused them to dog food and really improved the language itself. So there's a kind of really interesting lesson around that. The V8 team, they talked about how they wrote their thing in C++ as well. They spend over 80% of their time now dealing with security issues and not developing new features. All of that team would say that if they ever did this again, they would do it in a managed language or some language that gives them better safety. So that's why we're starting to get things like Rust. That's why we're getting all of these other languages. So even if you're not going managed, safety becomes a kind of key thing to this. So we start looking at, well, what really matters in our code? Well, the models we choose. But also, like, when I start to measure loads and loads of systems, I find so much time is spent parsing data formats, our choice of codecs. Like, if you really care about performance, please, please, please stop using text-based formats. XML, JSON, all this other sort of nonsense. You just waste CPU cycles, allocate loads of objects, and maybe as a side effect, do some business logic. If you actually profiled most of these applications written with text-based protocols and text-based encodings, you get to see that the business logic is almost like a rounding error you see in the profile compared to all of the stack of other stuff that's being executed. So kind of being aware of that. And then we're into what algorithms with data structures and sort of understanding the implementation itself. And kind of interesting, where do you focus and spend the time? So I'm someone who's been writing code professionally. I paid for my first software 30 plus years ago. And over that time, one of the things I've learned is stop learning all these new libraries. All these new libraries and funky things, they tend to have a life that is just so short it doesn't matter. Things that really matter is things like fundamental algorithms, data structures, understanding the platform that you're actually running on and getting the best out of it. Like learning things like coupling, cohesion, all of these good sort of things. It teaches you also how to write high performance code. It's kind of interesting. But we're moving into a world that is much higher core counts, much more distributed, and concurrency is now becoming a first-class concept. And when you start dealing with concurrency, one of the most important things to deal with is immutable data. And to deal with immutable data, you're going to be allocating quite a lot, and GC really is your friend there. So it's kind of interesting where this goes. So kind of quickly in closing here, again, think of what the future holds and where we're at now and we're kind of going to. I'm old enough to remember the assembly versus compiled language debate. I have a number of friends who write games for a living, and I remember going through that phase of where people were arguing about, do we use a compiler for our code, or do we write it all in assembler? And this has happened a number of times. It happened with the Excel team at Microsoft as well. And you get the people arguing over and over again that, no, we've got to write stuff in assembler because we can write it faster than any compiler can ever produce. But when you deal with a big program, you start to realize you have no hope of beating a modern compiler trying to write handcrafted assembler for a large problem. You may for a single method or a single function, but not for a large application. Now, are we starting to reach that same point for managed languages versus statically compiled languages? Here's an interesting one. Anybody here been to Brisbane, Australia? Anybody seen this screen? It was down there. This is a huge interactive screen. And it does different things. So it can be a waterfall, it can be fish tanks, this is rendered in real time. You can interact with it, you can touch it, and the water moves and fish react. And this is all being done real time, you're interacting with it. What language do we think this is written in? C, assembler, Java, any ideas? It's written in a language called Impromptu, which is a version of Scheme. So a bit like Lisp, going way, way back. It's got some nice intrinsics and a real-time garbage collector on it. And you can interact with this in real time. They've also done amazing stuff with music and other cool stuff. So it shows you what's possible. Like, if you can run a managed language and do that sort of thing in real time, why the hell can't we have web pages that render quickly and deal with them? If you see that, how impressive it is, and then you use some websites, God, they suck in comparison. So kind of think about, like, our time is not infinite. Where do we spend it? I'm not saying always use a managed runtime, always use static. Think about it, but don't just mindlessly go into the this whole debate and wars about is there pluses and minuses to things, because there are. There's lots of trade-offs and there's lots of interesting things that are happening in this space, and it's getting cooler all of the time. And on that, thank you very much.
While we are getting just the laptop switched out. Got it?
Yeah.
Perfect. Once again, thank you very much, Martin. I think that was a very, very good lesson on what modern CPUs can do for us, but also what modern languages can do for us. We have quite a few folks outside, so now's a good time to, as we transition, please find yourself some seats in the back, in the middle there, and please stay for the next keynote. Our next keynote speaker will actually show us how to use some of the modern new technologies that we got, say Chatbot, say serverless, say blockchain, and put it all together in actually a system to derive value for our business. Please give a round of applause and warm welcome to James Austin, Senior Director for Oracle. Do you need this or?
No,
okay. We are a little bit behind. So.
Am I on? I am on. Smashing. So without further ado, let's crack on. Martin brought up time. The one thing, apart from tax, that we know is going to be there in the case of time passing us by. Now, time is really, really important. Now, whether we're looking at latency or low latency applications and building out, making those right choices, or just making the choice of how to get somewhere quicker, using the time that you have to build better code, that is the key behind today's session, both from Martin's perspective, but also from mine. Some of the things I will be mentioning are, of course, bound by time. They're not yet released, but I will point out what they are, so please don't consider a commercial decision based on some of the technologies that we'll talk about today, because they're not quite there yet, although they are coming. Now, my time is spent talking to customers about a variety of projects that they have, and this is probably the first question that I get asked on a regular basis. There's a room here full of developers, which is awesome, and it's fantastic to see you all here. But aren't we just a database company? Well, no, we're not. Particularly, Oracle has been investing really strongly in the app dev space for probably the last 4 or 5 years at a pace where contributing to open source, getting into the cloud-native computing foundation and directly contributing to the Kubernetes project. Last year, and earlier than that, we were working on bringing our technologies into the Docker space so that you guys could take a trusted implementation of a Docker container and start using it just off the shelf from Docker Hub. We contributed Oracle Jet some time ago as a JavaScript extension toolkit into open source, particularly to just give you a curated set of technologies that you could choose to use. We open source Java, and we're going to see quite a lot today on the serverless proposition of FN, a project which is out of from the progenitor of serverless in the open source community. The FN project is a cloud agnostic serverless platform that allows you the flexibility to develop serverless and function-based capabilities anywhere, any cloud, on your laptop, on a server that you have, whatever. Now, the key common part across all of this is a shift, a seismic shift over the past 5 years, really, of Oracle doubling down in investment on open source, but not just putting in to open source, now having a focus on making it easier to consume open source. It's great that we have all these options to do, but to Martin's point about making time for us to make good decisions about the type of code we write and writing great code, why spend the time setting it all up when you could have a turnkey service that simply switches it on and allows you to crack on? Now, some of these technologies, from serverless functions in terms of the ability to shift the implementation and allow us to simply spin up a piece of code, let it run, and shut down. Some of us, the chatbot technology or the conversational artificial intelligence allows us to exploit some of these new technologies, particularly around the machine learning space. Instead of building it as a science project ourselves, although it's interesting, we need that time back. If someone's done it already, let's stand on the shoulders of that and start to use that. DevOps, we're seeing a lot of development moving from DevOps across into NoOps. So just having a platform that intrinsically knows how to build your code. So you spend less time building out a DevOps platform yourself. About 40 to 60% of a full-time equivalent is usually used within a 6-month project to set up the DevOps environment. Again, you're burning time where you could be building better code. The advent of blockchain is a fantastic example of a new technology that's come up that over the last couple of years has been experimented with by a wide range of folks. But when does it hit production? How do I get it from science project across the line into an enterprise kind of deployment? And more to the point, how do I just quickly get up to speed with it and be productive? And of course, the open source part I mentioned earlier, in that there are so many cool things with open source, but we do spend an extraordinary amount of time taking the next version and getting it going, and then having to tweak the things that I have in order to get it working. Why not take that away? So today's session, again, focused on time, is how do we combine these technologies to go build ourselves a solution and be able to do so quickly, effectively, and bearing in mind this won't necessarily be a latency-specific use case. How do we do that in a way that we can gain maximum productivity and get to market first? So let's take the case of buying and selling a used car. How do I know that that car is safe, that it's one that is genuinely owned by someone, that I have an audit trail of where that vehicle may have been, and perhaps I have an audit trail of the servicing and the provenance of the parts that are put in there too. So here's the use case. We're going to go sell a car with a combination of conversational user interaction or user interface. We're going to perform a set of checks through a very serverless environment, so I have a very dynamic way of making the checks on that car, and I'm going to, when I do sell it or buy it, I'm going to put the ownership of that car, because it's a valuable commodity, into a blockchain, so that I have an immutable pattern of where that car has been, who has owned it, and effectively the transactions that have occurred with it. And to make it nice and easy for even me to understand, here we go. 4 steps. Number 1, the guy with very strong investment in hair products starts out with a chatbot. And he says, hang on, I actually want to sell my car. Now he's going to go through and he's actually going to sell that car. But step 2 is, well, I need to perform a number of checks in order to be able to do that. And as part of those checks, I'm going to use a serverless foundation in step 3 to make those calls and to orchestrate them together. And Sean will be coming up on stage to show us how we do that with our serverless FN platform. And then step 4, we're actually going to buy the car back, but we're going to buy it from a different dealer. And when we buy it from a different dealer, of course, from a blockchain perspective, I want to see the order that those cars have been put in, who owned them, how they were moved across in a trusted transactional fashion. So for the noddy view, James is going to go ahead and sell a car, and I'm going to use a chatbot to do that. I'm going to perhaps use some kind of externally provided service for optical character recognition. I'm going to run it through a simple orchestration within a cloud service, and I'm going to call FN functions. And as part of that, it's naturally going to make those checks, but it's also going to talk into my blockchain and push the car, which is here, through John's dealership, and when I sell it, I'm effectively going to move it as a tracked entity through into the blockchain itself. And it will be identified as being owned by, in this case, John's dealership. Now, when I laterally come in on the other side and I buy the car from Bob's dealership, Bob doesn't have one of these cars. So how can he offer me the car that I want? Well, simple. He's able to interrogate the network within the blockchain, discover the ideal car for me, and be able to, through a smart contract, transfer that car into his own dealership and sell it on to me at a profit, needless to say. So let's crack on and show you what I mean. Is that going to come up? No, it's not. Let's try that. Okay. Try and get back into there. Marvelous. Okay. So, number one, I'll just prove that this is live. There you go. Fabulous. So we have some pictures, and we'll be able to see them as we go through. Well, let's start out with John's car dealership. Naturally, I've been through a test earlier, so this is not the first time I've been through this. So I'm going to start out the conversation, because I'm a nice guy, with hi, because I'm unimaginative, if nothing else. Now, the car dealership at the far end has a chatbot behind it that is going to interact with me and guide me through the process of picking the right thing to do with the car. Ah, excuse me. Turn that off. There we are. He's come back. Fantastic. So am I buying or am I selling a car? Well, today I'm going to sell a car. And one of the characteristics of Oracle Code over the last couple of weeks where we've been doing this across the world is that, well, we found a car that seems to lie around in our headquarters quite a lot. So, okay, let's find the registration plate of that car. And this is, there we are, that one. Now, this car, in particular, is owned by an individual at the top of our organization, which is slightly awkward. Which is one of the reasons why we keep buying it back at the end, because otherwise he starts to notice. All right. So it's gone off, and it's done a set of checks. Now, this is Larry's Lexus. And at some point, halfway through Sean's presentation, I will probably get a call or a text to say, dude, where's my car? And we'll have to start all over again. So having done that, having uploaded my pictures, the optical character recognition, the service that we've used has identified the right car. We've pulled down the right definition of the car itself. I'm going to have a look at the details just to check that it's the right thing. And that looks fine, yes. It's then going to make me, well, an offer based on the mileage, of course. So Larry, I think, had only done 800 miles, but having been stolen a few times during the course of Oracle Code, then it's done a few extras. So they're going to offer me, whereas the list price is $375, they're going to offer me $385. Is it okay with me? Well, yes, I stole the car and I'm fencing it. So that's awesome. So they will continue and send through those documents. So having done that, if I'm going to build out something like that, I could face myself with a very, very large task. And by that, I mean I could be spending a great deal of my time building code out, building the artificial intelligence underneath to understand natural language, and then programming and training and building all that stuff out. But in the greatest tradition of game shows, we don't want to do that. Instead, we want to provide you with a really simple way of grabbing time back. In this particular case, this is our bot builder platform. It's a declarative environment with a pre-trained natural language processing capability that behind here, we're going to assign a set of intents. So what is it that I want to do? Buy a car, sell a car, or in this case, say hello, the greeting. So when I sell a car, which I just have, what I'm going to do, instead of building out complex AI and going through a long-winded training exercise, I'm simply going to put in a set of utterances or a corpus of examples whereby that natural language processor will understand, your sell car intent, if I see a pattern that looks a bit like this, then I'm going to give you a percentage which matches up to it. It's not the same as doing something as you would build from the bottom with TensorFlow, because the outcome that you're looking for is that your chatbot actually replies with the right thing to you. So what are we going to do down here? Well, firstly, we're going to take that one. I'm going to press play, and I'm going to have a look at my intents and see how I do. So I'm going to say, how much for my car? Now at this point, I get a relatively marginal result, but actually it comes out with buy car. Now I don't want buy car, that's bad, because I want to sell a car when I say how much for my car. So I can begin to train it, add the example, choose my training mechanism, in this case the fast training linguistics-based model is fine. Yep, so sorry, the other one of course is a deeper one for production learning, but for dev, then I'll be focusing on the high-speed one, and I'm just going to hit train and go. Okay, relatively simple turnaround. So I've just added that one, how much for my car. I've just retrained it, so when I hit send this time, it's affected the outcome and said, yeah, that one's an exact match. But if I make a small change to what I'm saying, it's still able to identify from the patterns that are there or the linguistics that are behind it that, okay, whether it's my car, Larry's car, whoever's car, makes no difference. But the key here is that I've not had to build out a load of artificial intelligence and the engineering and science project behind it. I'm exploiting that technology. I'm buying time back so I can build a better experience, whether that's a better experience through the messaging platform that I have or a better experience from the interactions that that bot can give me or the conversations it's going to have. Either way, it's intended here to give us a very, very simple way of rapidly building out an incredibly powerful chatbot that can then be deployed to a whole range of different platforms. Or, as we refer to them, channels. Now, perhaps one of the most popular ones is going to actually be the web-based channel. But think about it like this. This chatbot capability is something you can deploy to the web. You can deploy into one of the many messenger platforms that are supported with an API, or indeed, you can put it into your own mobile application and have those kind of conversations. But the key here is it's really simple to build out very rapidly a really powerful way of interacting with your user base, but without having to spend your life building the underlying technology. So we've shown the bot builder. So let's go back. So today, we've just sold Larry's car. The text is probably coming in even now to chase up and to tell me that my P45 is in the post. But one of the things that it did in the background was do a Carfax check. So the bot itself was calling a set of APIs on the back as a result of the intents that I showed. So number 3 in this particular step is very much around looking at the way in which we're going to implement those functions. Now, we're not going to do a server-based run of this. Instead, we're going to go serverless. So at this point, I'd like to invite Sean up to run us through some of the details that go behind the FN project, which is something that Oracle has started out, released into open source, and currently has, what, 2,500 commits a month, something like that?
Large. I'm taking this.
You are? Excellent. Thank you.
I was told to take it.
There you go.
All right.
Thanks, Sean.
Thanks. All right. So, hello. Oh, hang on. I'm trying to press the button. We are challenged by technology. Okay. Come on. PowerPoint actually seems to be our biggest problem.
Well, they do say that, the only thing that
Am I in?
Everything works in PowerPoint except PowerPoint.
Oh, okay.
Oh, there you go.
Okay, thank you.
There you go.
It's all right. So, hi, my name is Sean Smith. I work on the FN project, which you described, James. And so we'll just jump in. So FN was a project we released at Java 1 last year. It's a bit ironic because it's actually written in Go, but we don't say that loud at Java 1. The core is in Go, but it's a multi-language platform. So it's an open source, Apache 2, runs functions in any language you choose to use. We have built-in support for some core languages. I'll walk through and show you how really easy it is to use. It's surprisingly lightweight, and that's kind of the point of functions. They're small, easy to write, easy to run. What's nice about the FN project is run it on your laptop, run it on some server in your data center, run it in the cloud, right? Which is our goal. I want to have the same code I develop on being what I deploy to, so I have very good fidelity between, if it works locally, it should work in the cloud. And a lot of functions platforms don't work quite as easily as that. So a function for FN is really simple. It's a piece of code, takes an input on standard input, writes your result to standard output, and logs to standard error, right? So it's one input, one output, one log, right? So you can imagine you're taking your application, you're breaking it up into smaller chunks. So it's sort of a microservices taken to the extreme, right? Rather than having a microservice with a large API with multiple services vended by it, a function does one thing, right? One thing only. And I'll show you an example. All the mechanics of how do I invoke that function, how do I get the code or the payload to the function, how do I scale up, all that's handled by the platform. So you can imagine I have a very popular function, I'm calling it a lot, having one of them isn't enough. I might have to have more. So the FN platform will scale automatically, adding more functions to handle the load. That's all just the mechanics. But from your perspective, it's serverless, right? It just does its job, takes care of all the code. You just deploy your code, call it, take care of the problem. So we're developers. We've written it for developers. It's got a very simple API. And it's got a very simple CLI for developer experience on your local machine. So the FN CLI, FN init creates the function. FN run it locally. So Docker's underneath the covers, and it's fully Docker-based. So if you know Docker, you turn on verbose mode, you'll see a lot of Docker commands going by. There's nothing magical. Really, it's just Docker packaging your functions. Run it locally on your local machine. You can test it local. You can deploy to a server. I'll deploy to a server on my own machine, but it's a separate server as compared to just running local. And call that function. And when you deploy a function to the FN platform, we currently expose it also over REST. So every function gets a REST or an HTTP endpoint, which we call a route. And I'll show you that. So let's just jump in. It's way more interesting to look at code to hear me ramble. Okay, bigger. Bigger. Okay. So I've got an empty folder here. I'll go FN init, runtime is Java, and I'm going to create a function called hello. Pretty quick. And what I've got here is a folder called hello. So we like to take the model of a function is in a folder of the same name. It's a simple organizing principle. You can override it, but it makes life easy. So I've got a Java function here. I could have said init runtime is Node, Go, Ruby, Python, and so on. We have built-in support for those. More are coming, but those are the core we're building right now. For Java, we're using, this looks like a normal Java program, right? So I have a POM, I'm using Maven. I've got a function, I generated a test, and I've got a funky YAML file. I'll show you what these files look like, so you can see how this works. And especially see the Java code, which is very surprisingly normal Java. So I have a funky YAML file. It's just metadata. It says I've got a function called hello. It's got a version, runtime. This is the class that implements the function, and this is the method that implements that is the function itself. And I got a couple of Docker images here I'm using for building and running, and I won't dig into that today. So I say we are Docker-based. So here's the Java function. What's cool about this is it's boringly Java, right? So there's nothing fancy here. You don't see any function sort of verbiage in here. You see a function that takes a string, or a method takes a string. It does the old hello world. If you pass in an argument, it returns hello you, whatever, or it returns hello world. It returns a string. I said before that an FN function takes standard input, standard output. There's a piece of code in here. There's the function developer kit for Java that's actually doing a bit of mediation between those sockets, or those streams, and the Java function itself. It's taking standard input, calling the function, taking the result, writing it out for you, taking care of it. And we have those for different languages. So it's easier to write a function than having to read and write, from those streams. But it's pretty boring Java, and there's a, which is a good thing, right? The tests are more, there's a full JUnit test support here. So here's a generated test suite, a test case for that hello world. Now there actually is missing a test, because this one will create an invocation of a function. It says this is the name of the class I'm going to invoke, this is the function. It calls it with no arguments, just get the results, and says if I call it with no arguments, I get hello world. What's missing is a test that says, if I call it with John, it should say hello John. But this is just boilerplate for you to get started, right? This is just code that's interesting to begin your work. All right, let's get over to run it. So I can go fn run, and I should try and get this thing up there. So fn run, we saw a building image. So behind the scenes, again, it's Docker. That function, that Java code got packaged into a Docker container and basically run locally. I can, because I have this whole thing with streams, I can say echo London, and I can pipe that string into the function, right? Very straightforward. Now that's running locally, so that's my developer experience. I can run local here. I can actually go into my IDE. I can run that JUnit test. I can get a nice local experience. I think it's working. I can now deploy to the server, and it's running locally also. Fn deploy. And applications belong to functions belong to applications, just as an organizer. So we have a collection of functions as an app. So I'm going to give it an app name. I'll call it London also. And I'm going to say keep it local. Normally functions will be pushed to Docker Hub or to your registry. If I'm working local, I can just keep them without dealing with the registry here. It's just much faster for me to go. So you notice it's deployed that. If I say fn apps list, I've got two functions there. One of them I just created called London. One I'll show you in a second called ocode. That London app is there. So I say fn roots list London. No, fn roots. You gotta be pair programming. When I say things out loud and I don't type the same thing, just tell me. My mouth and my hands are not agreeing, okay? Okay, so I've got this one function here, hello, and you see it is exposed over HTTP. Now I have a convenience way to call this. I can say fn call. The London application, hello, right? It calls it. I can also do the same trick with the piping of input. Same thing. London, hello. Right? So actually quite fast now. It's deployed. It's actually quite fast. I have a container running, rather than running it every time. Now, I do have the ability, though, to just use curl. Same thing, but because it's exposed, so all your functions are exposed as over HTTP. So I can go like this. You can imagine this is you have a lot of functions all available to you as webhooks, essentially. Very easy to integrate your functions with a lot of services that support webhooks. So it's the same thing, right? So that's a single function. It's very straightforward. Pretty easy. So let's take a look at the next step is I've got one function that's great, that's easy. What I really want to do is work with multiple functions. Where the function community is now at is really building applications out of functions. It's great to have a collection of functions, but you want to compose them together to build an app, right? Build something. So we've got fn flow, which is a way for us to organize your functions and sequence them, support fan out, fan in, all kinds of things to organize and deal with sort of how do I leverage that set of functions I've deployed. Today today the support is in Java only for writing flow applications, but support's coming for Node, Java, and other languages in addition. We built it actually on the Java Completable Features API. Anyone know the Java 8 Completable Features API? Okay, 5 in the front row. That's the problem. It's a really cool API for dealing with multiple threads, managing things. It works great for functions. Not that well known yet, but maybe Flow will make it popular, right? Maybe make it famous. So here's my scenario. Back to James's story, right? So I got this chatbot. My boss says, Sean, write this function, sell a car. Great. I'm going to sell a car, and then I'm going to basically pass over, to the blockchain to complete the transaction. But selling a car is much more complicated. He says, it has to do more than one thing. You've got to go check the Carfax. Was it, was it in a crash? Was it used in a crime? Was it used by the FBI, basically, in a crime? Was it, was it international crime? Is Interpol looking for the car? Maybe Larry.
I think he's on the
you know. Anyway, so this is what I want to do. Now, how do I organize this flow of control? Well, with Flow, I can basically use the Java Completable Features API to structure the flow of these, the control. I want to invoke the first function is going to invoke the second two, and then I'm going to do all the other ones. So I have you know, fan out, fan in, sequential, parallel controls. And what we do is we basically take that control and write a flow function. It's just a single function that says, call this, call that, call this, do it in parallel, do it in sequence, whatever you want to do. Just a simple single function. So with that, I can flip over and give you a demo of that code there too, and show you one more cool piece of technology. So we've got a little UI for visualizing the flow. So when you're running your functions, it's kind of cool to get a visual insight into what's actually happening. So I'll pop over there after I start this up. So I'm going to say, that's right. I'm going to call the flow. It's on the O code application I had running. So run that, pop over here, and we can see that the functions are running. I've actually slowed this down because obviously it's boring to go super fast. But you can see all the functions that are run, some in parallel, some in sequence. And you can see on the far right-hand side, we can tell what's to come. So we have an execution graph. We have a call graph that's taking place and getting run bit by bit. It's done. Now, what's cool about this UI, and it's kind of experimental, is I can click on a bubble, and I can go down and I can take a look at the full stack. Oh, yeah, this is a Carfax for a particular car we had found. This is a different car. It's kind of a neat UI. What's more interesting is when things go wrong. Of course, UIs are helpful. When things go wrong, I get a little red bubble. I can click on that bubble and get a look at the stack trace. Right, so how did I get here and what went wrong? Let me debug this, because I'm in a distributed system here. This is a bunch of different independent containers running in a fabric, and debugging it can be tricky. So this is a really nice tool. So that's a preview tool. And I skipped the code. This is actually the code that we had behind the scenes. I won't make you read it. We won't even skip through it. So what I wanted to do, quickly sum up, is just to say that FN is open source. You can go to fnproject.io, download it, try it. There's lots of tutorials. Actually, there's a hands-on lab today. Right after this, there's also a session later on today with giving you more details on FN. And we are working on Oracle Functions, a platform cloud service based on this technology that'll make it much more easy to consume. Rather than running it yourself, you can run it in the cloud. All right, James, it's you. Here, here. Yeah, just do that, close it.
All right. Sean and I had a discussion earlier about time. He stayed on time. There you go. That wasn't a killer. So that's good. Okay. Hopefully we'll. There you go. It's all connected up. So back with our scenario again. We've now completed section 3, where we've performed a number of individual independent tasks that have been orchestrated together using the FN platform. But what do I do with that car? Well, firstly, as part of that, I'm going to, as Sean just pointed out, push that into a blockchain to indicate that John's dealership now owns that Lexus. So, Larry kind of doesn't like his car going missing for a long time, so out of conscience more than anything else, that and self-preservation, I'm going to go back in and I'm going to go to Bob's dealership, because I don't like to go to my original seller or buyer of my car to go buy it back. So in the case of Bob and his dealership, I'm going to, again, being a happy chap, say hi and see if we can get that up, and we can. There we are. So this time around, I'm going to be buying a car because I've got a text from Larry and he's kind of annoyed about it. So I'm going to go find his car in the dealer network. Now, Bob has said I can have an Audi or a Cadillac or a BMW. Yeah. The trouble is, Larry kind of likes his LFA, so nah. I was thinking of a Lexus, if I can actually spell Lexus. There you go. Ooh, okay. And he comes back and says, I'm sorry, but I don't have a Lexus in my inventory, because, well, why would he? But in his dealership network, he's found a really nice car, apparently, and that is the Lexus that I sold into John's dealership earlier. So if I have a quick look at that, all right, yep, that one looks pretty familiar. In fact, I think it even has the same, yep, it has the same number plate, so it is the one that I sold earlier. Would I like to purchase it? Well, the pressure's on, so yes, I would. Okay, now this is the key. I'll transfer that car to my inventory from the participating dealership or dealer network, and then he can say, okay, I now have that in my inventory. Now that's where the blockchain has come in, because there is an arrangement between those dealers to be able to transfer those cars. So he says, that's interesting. That's the other interesting part about it, is he now has a 2017 Lexus LFA at $399,999. So he's making about $15,000 profit on this. So you can see perhaps that the transfer cost from John's dealership to Bob's may have had a financial aspect to it as well. But since I'm under pressure, I'm going to say yes, I will certainly buy that. Okay, and they want me to come into the dealership for a test drive and complete the paperwork and probably get locked up. So let's try it tomorrow afternoon. And he comes, okay, it's been a pleasure to serve you. Okay, awesome. And they'll see me there tomorrow at 2 p.m., which is probably when I'll get picked up in the process. So having gone through that process from a chatbot experience, we can see some of the implications of what's going on in the network behind us. And really, what we have here is a permissioned blockchain. Not the Bitcoin type, where everybody joins and has lots of fun and does a lot of proof of work in order to get involved with that network, but a permissioned network where enterprises can invite key members. So in the case of a dealer network, we're going to have a number of dealers that are invited to join that network. That cloud architecture, as we saw earlier, the car was already in there. When I ask Bob for a car and say, do you know, I'd like a Lexus, he goes off and he looks into this space, performs a transaction through a smart contract to say, what car have you got that might actually match a Lexus? And then having found one, he can then trigger a transactional process, again defined as part of the smart contract, to say, move that car across. So it becomes part of his inventory, and there's a transfer of funds or tokens of some sort that goes across there. And our little car ends up moving across to me in the end. So what is this blockchain? Well, number one, okay, who in the room is aware of blockchain? Okay, so this explanation is largely moot, but for those of you who just want a swift reminder, it's about maintaining a set of data across a vastly distributed network, giving us some level of near real-time interaction in a non-repudiable format and an immutable format of data that's shared across a number of participants. When it comes to it, it comes down to one thing: trust. It replaces or enables the trust between two organizations by putting a contract in place that is embedded in the very nature of that technology. We found there are a whole range of areas of interest everywhere from where you may think, like financial services through supply chain. So, for example, a large supermarket chain may be slightly worried that its lasagna actually has horse in it, so they want to make sure that, in fact, they definitely have beef. In the case of public sector, there's been something that turned up recently about the land registries, where it was possible for a legal authority to come in and sell a house from underneath someone. So there was one guy who opened his front door one day to be told by the guy outside, I own your house, and he had proof. So being able to put that immutable ownership session and control of transactions in place is key, certainly for that guy. I've got to say, I did smile when I heard that, but then I put myself in his shoes and stopped smiling. Likewise in healthcare, being able to maintain records, immutable records that go on, that allow us to see the full history as just part of the innate design, or the innate design of blockchain itself. So how are we using this? Well, what we have done is we've got involved with the Hyperledger project, and we have contributed to it as well as using that technology, and we're simply implementing it. We're making it easier for you to uptake it. We're taking the validating nodes and the peers and simply deploying them to 3 separate availability domains within our cloud. Ledger-wise, we're putting in one of the pluggable database choices that Hyperledger gives you. We're putting in Barclay. Smart contract and chain code, of course, making it easier to apply that, because there are a number of ways in which you can. So starting out with the smart contract implementation that's available in Hyperledger and simply implementing it within a platform. Making an offer of an ordering service so that we can ensure that those transactions happen in the right order. And going from there, the membership service. Because when I invite somebody, I want to make sure that they are the person that they say they are. And I want to give them a certificate to prove, as part of their interactions, who they are on an ongoing basis. Strangely, blockchain isn't an island. It's going to be part of your app dev landscape, whether you use it in your applications, on your mobile device, or in any application integration at all. We're going to need some way of getting in there. So we've introduced the REST proxy as an extension to the standard SDK. Added in an administration console to make it simpler to visualize what's happening in that space as well. And of course, offering all of that as a managed PaaS, a turnkey, there you go, get started building your network. Don't worry about which orderer I'm going to use and how I'm going to implement this and how do I make it resilient. It's done for you. It's saving you time. You turn the key, you get going, and you build your blockchain. You start integrating into it. And that, of course, is where the applications that you're building are going to come in, whether that is through the SDK that's provided by Hyperledger, which of course is still there, or straight through the REST API just to do it quicker. Now, as a developer, there are kind of 3 areas that you're going to want to consider. And those 3 areas are broadly the application that you know about, the ability at the top to define private networks in which those members will interact, because I don't want, as a car dealer, for all the other car dealers in my network to see every transaction that I have. But I do want to be able to make sure that I have a private channel between me and the end dealer. And of course, writing chain code or smart contracts within there as well is the 3rd key area. And if those 3 are the key focal areas, the rest of it's provided for you that you can choose to scale dynamically, to define the network dynamically, and to just get some progress. So we'll wrap up with a quick demo of this. Whoop. Okay, if we get the size of the screen right. Let's have a look at the last month. So this is our out-of-the-box console dashboard. We have 3 organizations in there: Detroit Autos, John's dealership, Bob's dealership. We've obviously executed a number of transactions that have gone through there successfully, but critically, we have only one set of chain code that's deployed to a particular channel. Oh, that was the wrong button. But I can start to dig down deeper into this. And as I see, I have my three organizations. One is a founder. The others are participants. And those participant nodes or peers can live outside. And to give you an idea of what I mean by a peer, we can choose a different way of looking at it. Each of the blue blobs is a member that's been inducted into my blockchain. Each of the green blobs are the peers that represent those members within the blockchain and perform processing, but also hold a copy of the world state as well as the history. And of course, the red and the blue, we have both a membership service and we also have an ordering service as well. Now, when we start to look at the nodes within there, we can look at it from a very technical standpoint, or we can practically look at how have I configured my network. I have a dealer channel at the bottom, Bob's channel, John's channel, the Detroit orderer channel. So I'm able to separate the conversations that I have, be able to share it across a consistent network, but really separate it by private space as well. And then right at the end, I'm in a position where for my dealer net, I'm going to deploy my set of chain code which defines how John and Bob are going to transfer that car, or how the car gets pushed into the blockchain. I'm going to do that on my dealer network, which shares all of my members. So that is how I'm going to control and manage and govern the interactions between each of them. So, in the interest of time, we will press on. I guess the key here is that these technologies are not islands, but there are incredible ways in which we can save time, lots of time. One of which is to be able to bring together an entire app dev space with a set of tools that are consistent across one particular platform, delivering everything from CI/CD through an autonomous lifecycle management and predictive monitoring. So you can choose to get down with the code that you want and spend less time building out the infrastructure, the resilience, the backplane, all of those pieces which are going to be highly repeatable, to say the very least. Now, Oracle isn't just a database company. We're providing front and back-end tooling, a common set of tooling from container-based cloud services through to API management platforms. And of course, you've seen the chatbot capability, the blockchain elements coming together with FN as a set of underpinning app dev technologies that you can use to get somewhere faster, to deliver your result more quickly, and frankly, get to market first. But we do, as part of our step forward into this open source acceleration space, we want to hear more from you. That's why you're all here today. That's why we are here, and we wanted you to come. We want to meet up with you. We want to understand more about what you have, what can better give you that time back and allow you to focus on the things that matter. Please do come and join us at the London Developer Meetup, which is planned for, which is actually planned according to the bottom side. It isn't all Oracle, right? It's going to be a combination of technologies and views and feedback and discussions that are going to really feed both sides, I think, of the discussion. So please come and join us in London. And if you do nothing else today, if you want somewhere that's going to go, perhaps just save you a little bit of extra time each time you go there, if you go to developer.oracle.com, we have a wealth of content that we're pushing up there that our ecosystem is contributing to. So if you do have a little time and you go to developer.oracle.com, then I'm convinced that that in itself will, each time you go there, save you just a little bit of time in your everyday work. So with that, I'll say thank you very much.
Thank you very, very much, James, and thank you, Sean, also for the demo. So just before I let you go, a couple of housekeeping slides. I'm not going to keep you much longer than 5 minutes, hopefully. First and foremost, Oracle Code would not be possible without our sponsors. A big thanks to all of them, especially the UK OUG and Redgate that are out in the Developer Lounge. All of you have walked through the Developer Lounge coming here to the auditorium, the big space. So please come, go over there and say hi. With a couple of announcements or releases that just happened, in case you aren't aware, we just released Apex 18.1 last week. That's our low-code platform that allows you to build stunning applications fast. So go and check that one out. We also have released Java 10 about 2 months ago. So that's the first release under the 6-month release cycle. Go check that one out as well if you haven't yet, and certainly also check out the completable APIs as we've heard before that we got with 8. GraalVM is a new Java JVM, open sourced, up on github.com, Oracle/Graal. It allows you to run any language within the JVM. It's already in use in Twitter, so if you want to hear or see more about actually the managed language capabilities that Martin has talked about earlier, go and check that one out. And we've also released MySQL 8 about a month ago, which has brought quite a few more capabilities to the JSON support or the NoSQL style of applications, but also has gotten much faster and some more analytical SQL functionalities, so go check that one out as well. Just recently, 1-2 weeks ago, we have released a new version of the Visual Builder Cloud Service. Visual Builder Cloud Service essentially allows you to write or to produce a very quick and nice looking JavaScript UI based on any REST service. It just takes REST services and you can then visualize those. So if you have those use cases, go check that cloud service out. And we also got the developer cloud service, a new version that just got out. That's not only if you are happening to develop in the Oracle Cloud, but also if you just want a service that gives you a Git, that gives you some Wikipedia style or some Jenkins style tooling, you can go and use the developer cloud service on Oracle Cloud. And we're also very excited that we have just launched our Oracle Container Engine for Kubernetes, or short OKE. We're always very good at names, as you probably know. So that's also now up on the Oracle Cloud as well as the Oracle Container Registry. That's just with announcements of new products. If you would like to learn more in a self-paced fashion, the Oracle University offers actually a promotional code for the attendees today. If you go to education.oracle.com/code day, you actually get a promotion where you can then sign up for whether that's courses or trainings or certifications and so forth. So certainly if you want something self-paced, MOOC kind of style, go and check out that URL as you hear all at Oracle Code today. We got Simple App competition going on in the Developer Lounge. Those are short, tiny, short hands-on workshops. And we got this competition go on throughout the day with a leaderboard in front, and whoever will be on the top at the very end today will win this Bluetooth speaker set. We also have the Oracle Death Star Challenge going on as well, just next to it, and some of the top winners will get a nice little lightsaber as well. So obviously I'm not giving that one back. So go and check that out as well. James and I always kind of compete with the same slide on developer.oracle.com. Our portal on the web for anything developer related, as I said, go and check that out. Last but not least, or almost last but not least, so we are about to wrap the keynotes here up. The developer lounge is open. We have a short break for about 20 minutes going on. The sessions will start at 11:15. Same with the hands-on lab as well. Once again, the app on your phone is probably the best way to navigate across all the different sessions. And then at the very end of today at 6 o'clock, we have a very special session going on. Dr. Sue Black is actually giving an inspirational talk about how to succeed in the world of IT. So regardless whether you just got started in IT or you're in there for a long, long time, Sue is a fantastic speaker and will share some of her experiences of how she actually succeeded as a technology evangelist. It will be back here at 6 o'clock in the auditorium. Thank you very much, Sue, for doing that. And the very last slide, so if you would like to try anything of the new exciting technologies out that you have seen today throughout Oracle Code, you can do so on Oracle Cloud. If you go to oracle.com/code500lon, LON, you have also the little ticket in your badges, I believe, in the back. You will get a free $500 trial for Oracle Cloud. And with that, I would like to thank you very much for showing up to the keynotes, for sticking through the 2 hours, and I would like to wish you a very good and successful day at Oracle Code London. Thank you.